Hello everyone, welcome to Engineers Ireland. We are going to look at the second chapter of differentiation today. Once we get through that, we'll be moving on to the question in part B, paper 2, the one on calculus and series and sequences. Now, you have at this stage covered all of the sections that will be able to make that special question very easy once we finish this one, of course. So then, differentiation 2. The main thing about this chapter is that we are beginning to apply differentiation. There isn't much by way of new stuff in it, by way of new theory, but there is a change of approach and emphasis. We also get back to something that runs through about 4 different chapters of your Leaving Cert course, which are limits, and you'll again find that they're extremely useful. But anyway, to begin with, I suppose we would say from a mathematical viewpoint what we'll be doing is fitting curves and finding interesting features like turning points and stuff like that. So what is a turning point? I suppose that's the first place we need to go to. We look at a function like that, we can say that at any given point, like here, you can find a tangent, and we all know that you can find the tangent to a curve by differentiating the curve to get its slope, and if you know the point, you plug it in and you get the straight line. So we're looking at this and we're saying this thing here, that is quite a big positive slope. This one over here, it's positive all right, but it's not as big a slope. And if we come down here, we can see we've got a negative slope. And that means somewhere along here we've got slope, which you can call m if you like, is equal to 0. That's a place where you could say the curve or the slope comes to rest. The slope goes to 0. And looking at that graph, you said this is at the maximum, because a bit like climbing a mountain, while you're still climbing to the top, you're still gaining, you're going up. Well, when you're on the way back down, the slope of your journey is negative at that point in time, and you've already passed the top. It's only at the top that you would have no gain and no loss. The same equivalent thing happens heading down towards a minimum. Negative slope. And when you head away from it, you get positive slopes. And right at the minimum, you'll get m equal to 0. Okay. There is a third place where you get a 0 slope. It's called a saddle point, and we look at that separately here. Something like this. Clearly you can see that we have a positive slope here, and over here we have a positive slope. Now obviously there are curves that will go this way that'll have negative slopes all the way along them. Now the interesting thing about this one is you get to a certain point where curvature that has been happily running away in this direction, where the slope is actually, the rate of change of that slope is decelerating, but unlike the peak up here, which had been doing the same thing, once the peak got to the top, it changed from going up to going down. This, for some funny reason, changes its mind and decides to go and continue up the way. In a case like this, you can actually get, now this is not very well drawn, so please forgive me for this. I'll try and do a better job of it. You can get one particular tangent. Well, it's technically hard to call it a tangent because it actually cuts through the curve. You'll notice all of the other tangents where they touch at one point and they don't cut the curve, locally at least. Down here we get a slope of 0, and it isn't a peak and it isn't a trough of a curve, it is a saddle point. So then, what have we found now? We found 3 different types of places where slope goes to 0. If we're given a particular equation of a function, and we're asked to sketch it, find its peaks, its troughs, we have to have some means of being able to distinguish and to be able to know whether we've got saddle points and stuff like that. For example, and just to pick a very simple one, we can go we can first off always find a tangent, because the dy dx is equal to slope, which we've been calling m, and we would say to ourselves that's 10x plus 3 cos x. At any point, and in this example here it's 0, 2, we can find slope by simply subbing in to this particular thing here. So at any given point in time we can find the slope. We would want to find peaks and troughs because they're very important. They're significant points in a function. All we have to do is to set a slope equal to 0. You can see the slope here at this particular point gave us a 3. We can actually force the dy dx function equal to 0 just to give us our slopes. There's an important little point that you should keep in mind here. We know that this e to the x, it can't be negative, it can't be 0. It's like having x plus 4 multiplied by a 5 or by a 7 here. That's a positive number, so you can just divide it through and we can say that implies we know that we have a slope of 0 in this particular function when x is 4, and the value of the function is minus e to the minus 4. So this is very useful. What are the issues? And most of them actually relate to this guy. We don't want to start confusing ourselves with saddle points. There are two ways to approach this. I'll start with the method that generally you see in school, and it works for almost all of the time, but there's an occasional time when it doesn't work. Stationary points, slope equal to 0. Local max, we've seen that, local minimum, and the saddle point, which is also called a horizontal point of inflection. Let's just discuss the saddle point and other points of inflection. Here you will generally have a tangent, and in the normal way, it's hard to write with this, so I keep mucking up the graphs, and in the normal fashion a tangent touches at a point and it stays on the same side. A point of inflection is a point where the tangent actually cuts through the curve. It's a very odd point. In this case here, you'll notice the slope of that is not 0. When the slope is not 0, it's just simply a point of inflection. In the example that we looked at in the previous page, clearly this is a horizontal point of inflection, which has got the general name of a saddle point. So what do we normally do with these? For a local maximum, we differentiate twice. And when at the point that we find, when we've gone our dy dx and set it equal to 0, we might get 2 or 3 different x values, and we'll say, okay, which of those actually has a max, which is a min, which may have a point of inflection. So what we want to do is we'll differentiate twice, and when we put in the particular value of one of those things, if we find that the answer is less than 0, it's a max. Now, you might think in your mind that when d2y dx squared equals 0, you can definitely state it's a saddle point, but the reality of it is, and this is the point, that the test fails. What do you do when the test fails? You go to the alternative method, which doesn't use the second derivative. I'll show it by way of a tabular example here. For a particular function, we will have got certain results. We'd have gotten a 0 when x was minus 1. We'd have gotten a 0 in this function when x was 1, and another 0 when x was 4. And we're trying to establish now whether we've found maxima, minima, or point of inflection. And the trick is, you actually go 1 point below the 1, to like minus 2, 1 point above the 1, and we find out what the slope value is. Now, if this slope is positive here, and if it's negative here, we can go back to our little graph again. What we knew was it starts positive. We know at the peak that it's 0, that's the minus 1 kind of effort, and we're back into a negative. So it started positive, it went to 0 and went negative. So we can say that was a max. If we now go to the second point that had a 0 slope, one below it happens to be the same point, it happens to be 0, which is kind of handy. By the way, it doesn't have to be exactly 1 below it, it can be 2 or 3 below it, so long as you haven't crossed over one of the other points that you found. Like in this case with minus 1, 1 and 4. So long as you stay in between those, it's okay. So now we're looking at this particular one, and we already know that it's negative below it. If we find that when we put in the value 2 into the function, into the dy dx, and if the answer is plus, we've gone from a minus to a plus. That means the slope would have gone this way and then gone that way, haven't passed through the 0. So this then is a min. The last one then, for the value of 4, I'll try and squeeze it in up here. We already have confirmed that at 2 that we have a plus slope, we have 0 slope here, and beyond it we also have a plus slope. So then, that's a saddle point. You get the idea? If we have found this to be the case, that d2y dx squared for any one of the points, and here it would have definitely been the case when x was 4, we got a 0 in the dy dx, and if we got the d2y dx squared, we would find when we put in 4 that we'd have got an answer of 0 and the test would have failed. We would then go back, draw a table like this, and just check one or two other very simple numbers and find out what their slopes are. So to begin with, we had minus 1 was one of the points we found, 1 was the other, or another, and 4. Each of those gave us 0 slopes. This type of thing, a 0 here, 0 here, and here. Make it more real for you. you go one below the value, you go one above the value. When you go one below, we found a plus slope, one above it we found a minus slope. So we're looking at this type of condition. So that's a max. The next one, when x was 1, we had a 0 slope. One below it, you've got a minus slope. One above it, you've got a plus slope. And you're into this condition. So that's a minimum. And up here, for number 4, when x is 4, you have a plus below it, a plus above it. So it's a saddle point. Similarly, a minus below it and a minus above it would give you a saddle point. Let's just look at a simple example on this. We found that there are two values that gives us a 0 slope, when x is plus 3 and x is minus 3. So let's do the second derivative version here. Why do we use the word local? Probably best explained by a drawing. Here, there's clearly a local there's a maximum, but there's a bigger maximum over here. But in this particular part of the graph, this location, we do have a local maximum. Just because it's not as big as that maximum doesn't matter, okay? There's a little point I would just like to add here, and it shows up in an example in Rowntree's book. When we differentiate the particular function, and we got, in this example, minus 2x plus 12, we can say that implies d2. And don't forget, f of x is just another name for y. What that is telling us is that everywhere in this function that the second derivative is minus 2. It's a constant. Now there's no need to worry particularly about that, because what it means is that if it's a minus, we expect that if we have found a slope of 0 up here in the ddx equation, we automatically know that it's going to be a maximum. So x is 6. When x is 6, we're saying there is a max. We know that because at all places in the f of x curve, the d2 dx squared of it has a minus 2. Therefore, having found a location where the slope was 0, that must be a local max. So don't get concerned if you find that the d2 dx squared is a constant. If it's less than 0, you're saying to yourself, I know there's going to be a max when I find a slope of 0. If it happened to have been plus 2 instead of minus 2, you know it would have been a min that you'd get. If d2 dx squared of the function gave you a 0, you know this method working this won't function, and you go back to the other method, which is just get the ddx of the function. And if we had assumed that in this case here it wasn't minus 2, that it was actually 0, we would, and having found an answer of 6, we could have said x, we'll put in our 6 here, we'll go 1 below it, 5, 1 above it, or whatever number you feel like, and we'll say the ddx of the function, we know it's 0 here, and we will just check, what is it, plus or minus? And depending on those answers, you'll know if it's a max, a min, or a saddle point. My maths teacher, when I was in secondary school, was also a Greek scholar. The reason I mention that is I can never, to this day, remember whether he used to call asymptotes asymptotes or whether he used to call asymptotes asymptotes. Most people I know call it one. I generally will call it asymptote because it's actually a nicer sounding word. I'm not sure if that's the one that most of you know, because I've always been confused as to which word. I believe it has its roots in Greek, but I'm not a Greek scholar, so I don't know. What we're looking at now is another aspect of being able to graph a function, or know important things about it. Some functions have a very odd characteristic. For example, if we consider this line here, we can say to ourselves that as x gets nearer and nearer to this particular value of x, this function is getting closer and closer. In the case where this function never passes to that side, where it just always, no matter how near you get to here, gets closer and closer to this, then you'd say this is an asymptote. That's a vertical one. Naturally, there is an equivalent horizontal one, and some functions can be drawn like this. Where they have both a horizontal and a vertical one. I don't expect I'll get a medal for art, but there should be enough information in this to allow you to see the point. As x goes to minus infinity, this function gets closer and closer to the asymptote. As x goes to plus infinity, the function gets closer and closer to the asymptote. And for a particular value, which we will just say is a here, as x gets closer and closer to a, the value of the function gets closer and closer to the blue line. That's from a bigger value of x, and from smaller values of x, it's also getting closer and closer to that line. So what we need is a means of being able to work these things out, to find out horizontal and vertical asymptotes. The easiest one is the vertical one. These guys here. This normally occurs in functions of this type. Rational functions. When g of x equals 0, y is undefined. I'll change that to a at the moment. For a particular value of x called a, when g of a is 0, y is undefined. So it's easy to work those things out. Example. So when x is 2, we've got a vertical asymptote. So in that case, we would be looking at a value of 2 there. And you'd have a vertical line, which would be your asymptote. Horizontal. To work out the horizontal ones, we need to return to the limits. And it's easiest to describe this by an example. I would ask you to revise the stuff you covered on limits when we were dealing with series and sequences. What you will know from this here is you look at the x values, you find the biggest power, and if it's the biggest power, it's at the bottom, and in this case it happens to be the same top and bottom. You can divide through by it, so we'll say it's the limit as x goes to infinity of 2 plus 3 over x all over 1 minus 2 over x. We had a rule for any power p. We're basically saying that the limit of 1 over x to the p goes to 0. So now we can actually Get rid of those. So we can now say that we have a horizontal asymptoty, and the value of it is y equals 2. Because after all, this is a value of our function, so we're saying y equals that. At this point, you actually have all the little tools that you need for working out and drawing up a good graph of a function. Now, checking for asymptoties is very easy. The differentiation that you're dealing with here generally doesn't have functions as complicated as you would have gotten in the first differential chapter, because the first chapter was learn methodology. This chapter is more got to do how do you apply that methodology. So what you will often find in cases like that, in the applied one, the mathematics that you're given is simpler because your emphasis is on application. So we shouldn't have any great difficulty with these. Now, let's pick one example here. So we know that we have got horizontal slopes, in other words horizontal tangents, when x is 2 and when x is minus 4. What we have to figure out is, are they maxes, are they mins, or are they points of inflection? We can obviously use the tabular version, and this is what's being used in the example here. Notice that you aren't going for evenly spaced values. You just want to find at least one value in between both of these, and you'll want to find one on the left of that and one on the right of this. So this is one of our interesting points, and that's the other one. So we're saying now, what do we get by way of slope? We know it's 0 here, and we know it's 0 here. It's negative there, it's positive here. So we can now say, if it goes from negative to positive, that's a min. And over at 3, it's positive. So this is a saddle point. If we are looking at asymptoties, we can clearly see that the function we started with isn't one function divided by another. It isn't rational. So there goes our one of our type of asymptoties. And what we can also see is that we get nothing out of the other one either. So when we go to draw this thing looks like what else would you have found out for this? You would have found out when x is 0, what value do you get? You would have found out when y was 0, what value do you get? You'd get that one and that one. So those three come straight out of that equation up here by just setting either x or y equal to 0. And we will have also found out that our saddle point here happens to be coincidentally with a point where it's crossing the x-axis. That's an easy example. Let's pick a harder one where they're asking you particular questions, where you have to prove certain things. For all x elements of R, but x not equal to -2. And there will be asymptotes here. You're positive of it because we do have a rational function here. Now, they want us to do three separate things. One, prove that the graph has no turning points or points of inflection. Okay? That's the first thing. And we'll start with that one, I suppose. Vertical asymptoty. When we work out the ddx, when we differentiate the function, we actually find that there is a perfect square in underneath here, which is nice. It's always worthwhile keeping an eye on that. One of the things it tells us is, because this is a perfect square, it's telling us that this must be greater than 0. Clearly, you can see when x is -2, you shove it in here and you've got 2 over 0, which is undefined, but we've already established that to be the vertical asymptoty. So neglecting that one point of x equal to -2, for any other x value, because this is a perfect square down here, that's always going to be positive. So in all locations the ddx of f of x is greater than 0. There is no horizontal slope. Therefore, we've already proved there's no turning points or saddle points. In algebra, you will remember how important the proof of, working out perfect squares are, and it's not surprising that you'll find it in this. It turns up in a number of other chapters also. But it's one thing. It's a bit like looking at the differences of squares or the difference or the sums of cubes. They're things you should always look out for no matter what chapter you're in. In this one here, had you not thought in terms of the differences of, the perfect square, and that for all real numbers it'll be greater than 0, except of course where you have the asymptoty here. If you didn't, you would have difficulty here. Now, What else are they looking for in here? The second thing they've looked for okay, where does f dash of x, where is it less than 1? Now you'll notice I have to move back up the page simply because I'm trying to use as much of the space as I can without having to click and lose everything that's here. Naturally, when you're doing your maths, you keep progressing down the way. So we're looking at this, x squared plus 4x plus 2. You find the roots on this. So they're going to give us 2 points. Now, how do we know whether it's going to be greater or less than? Okay, if we can basically state that on a horizontal line. Now I've got a point down here and I have another point here. Just to absolutely be certain, we can put an x value of 0 in here, and we would go, that'll be 0, and this is 2. So we're saying that's definitely greater than or equal to 0. So we're happy with the space in between our 2 points. We'll do a small graph down here. What have we found out? We found out asymptotes. And we can find a number of simple points. When x is 0, what values do y have? When y is 0, what values do x have? And they will lead us to this curve. We just have to sketch this function. We don't have to be accurate everywhere, but we do need to be accurate in a number of places. We need to know where there's a max, if there is one, where there's a minimum, if there is one, where there's a point of inflection or saddle point, if there is one, and definitely where it crosses the x-axis and the y-axis. Those points you have to be able to work out well. After that, then, you simply curve fit. This, I've always found, is one of the nice bits of the Leaving Cert maths, because from a small amount of information, it's amazing just how much you can actually work out. You will notice in a lot of the cases that we've been dealing with, whether we were dealing with algebra or you move on into geometry, functions cross the x-axis. Now, up to now, the type of functions we've been dealing with have had nice tame crossing points. For example, when you're dealing with cubic equations and you were asked to find the roots, which is basically finding where it touches the x-axis, there was always one easy one. It could have had a value of 1, 2 or 4 or 0 or something like that, or simple negative numbers. So you could guess one and then that would bring it down to a quadratic, and you could work out the two complicated ones from there. In this section you will find equations where that isn't true, and where if you tried to do that you would just waste your time. So what we're looking at is roots. So we're now actually back into a part of algebra, but a part of algebra that needs some help. What you will notice though, and we're about to move on into one of the nicer sections, or little subsections in this, the Newton-Raphson method, and for some odd reason people find it complicated, but what we will do is we will appeal to geometry of the line and hopefully make it simple for you. The idea here is that there's a function, and for some nice round value, let's say like 5, you're below the line, and for the next nice round value, which would then be 6, you're above the line, and somewhere in between the function crosses the x-axis, and it isn't a handy thing like a half or a quarter way between them or anything. We need a method of working this out. So what do? Basically, you guess. And the easy thing is you'll know some location where x is a, another one where it's b, and you know it's gone from the y value, has gone from a negative value up to a plus value. Pick this guy as your first guess. If it was the root, we know the function at b would be equal to 0 if it's a root. But unfortunately, it's not. It's a positive number, but it's a guess. Now what we need to do is to find a better guess from this. What does calculus tell us here? We already know a number of things. You know that a tangent to the curve there, we can get its slope by differentiating the function, and we also know the answer of the function here. So then, what does geometry of the line allow us to do? It's the value of the function when x is b. I can differentiate with the function that I have. That function, and I can get f dashed, which is how we're going to talk about it now. And I know that for any x value, if I put in the value into the f dashed function, I find the slope. So if I started off with a guess called x equal to b, the slope is f dashed when x is equal to b. So I found the slope here. I also know a point on that tangential line. The point is b, f at b. So I can come up with a straight line. What does that straight line look like? The standard ones, okay? This is the tangent. we know the standard equation is y equal to mx plus c. So we're saying, okay, we will know our slope, and we can say the function at b is equal to f dashed at b by x equal to b, and now we can work out our constant. We can find out where it hits the y-axis, so that implies the constant is equal to that's easy. That then allows us to write our equation. Okay, all we've played around with now is geometry of the line. How does that help us? Now, I know this is a section that's it's covered in all schools, but what I'm trying to do is to give you an alternative way of looking at this, because a lot of people actually have great difficulty with the Newton-Raphson method. All I'm showing you is if you go back to stuff that you would have been doing in second year in secondary school, that you will find that you have all the tools there. Once you understand that the slope of a line is actually, of a tangent is actually the f dashed of the function, we have all the tools we need to be able to think our way through the Newton-Raphson. What we will do now is draw this graph in a little more detail. We had made a guess. The guess was that when x is b, this function crosses the x-axis. In other words, we have a root. We were wrong, clearly, because the f of b is not 0. But that doesn't mean we just have to take another wild guess. What we're going to do, and what we are doing, is we're appealing to geometry of the line. And the geometry of the line says to us, well, if I forget for the moment about this black function that I'm actually really dealing with, if I forget about it, and now pay my attention to the tangent and say, we'll make a little assumption that where the tangent crosses the x-axis will be where the function crosses the x-axis. Now we know that's not true, but we should be closer. What we're going to look for now is this point, this one here. Having found this point, and we find it by doing this, we'll just call it C. We find it by letting the y value of the tangent equal to 0. All this is 0. And now we have found a means of estimating this point. Will you forgive me and allow me to do one thing? I'll call this point D, because I realize that over here I've been using a C already. So we're calling it D. We can now say D is equal to I'll get it in the order they have it here. Okay. Yeah. That's interesting. Now we're deliberately avoiding the xn plus 1 terminologies, so you'll see how easy this game is. All we've done, just to recap, is we have an idea of our function. We've made a guess to find where it crosses the x-axis. We know three things. We know obviously what our guess value was. We know what the y value was, so that's a point now on this line, and we also know the slope of it because it's the f dashed. That allowed us to go down here and start off with our basic lines, and we say y equals mx plus c. So what was the y value? The one of the point we know, it's this. The x value is b. The slope is f dashed, and that gave us the intercept on the y-axis for this tangential line. That gets us to this equation. It's just this equation of a straight line, and we're saying fine, I have this equation for the straight line. Now I'm going to look at the bigger graph and say where that one hits the x-axis would be a very good guess of where the main function, the f of x, will hit it. So we've now gone and worked this out. We have said this point D, or this x value D, I now have a means of calculating it. It's the previous one minus the value of the function for the previous one divided by the slope from the previous one. That allows us to play a very interesting little game here. We will now calculate a new value here. That'll give us a new tangent. That'll let us calculate a new value, and we keep going. So we start to step, and eventually you will find that this series of jagged steps, which run like that, up here, that, up here, that they'll get us to a point where the value of the function is so small that it could be taken to be 0, or it's small enough for us to call it 0. All we have to do with these now is to replace our terminology with the one that's in the book. Our first example value was x equal to b. Now I can say that's the xn one, and the function at b will be the function at xn, and the f dashed at b is now f dashed at xn. And what we have found is that the new x sorry all that has been arrived at by just using the equation of a straight line, which you've been using since second year. I apologize if using A, B, C's and D's have actually confused things for you. But what I'm aiming to show you is that part of the reason, at least that I believe, that people have difficulty with this is because we're using xn's and xn plus 1s. We've just shown how starting with one estimate of x led us to the next estimate. We just can then say that estimate then, find the tangent, find where the tangent cuts the x-axis, use that new x value, and we run on, and we will get something that you will get yourself down to a point successively, and you will notice these are actually getting there very quickly, eating up the ground. So that's the game. Newton found himself in another very vocal exchange when this came out, because he had actually worked it out maybe 20 years before a guy called Raphson. But Newton had hid it because he had learnt his lessons and found how humiliating it could be to be ridiculed for calculus. So he came along with this particular thing and he buried it in one of his books. It was there, definitely. He had to have known the methodology. But Raphson published and he had great applause for it. Newton then came out, and it took quite a length of time for him to argue and to win his argument that he had had the method beforehand. So it was agreed that both of their names would go on this. As it stands, I've always thought that they should have put Raphson first, because he at least had published it first. Having discovered it is one thing, but if you were in science or in mathematics, if you discover something, you write a scientific paper, you publish it, allow your peers review it, and the first to publish has good grounds to claim the thing for their own and to put their name on it. I think it should be the Raphson-Newton method, but that's just that. Now, we're very near the end of this chapter, you know that. There's only little easy bits left, and we can go through them very quickly. The Newton-Raphson comes up fairly often. If you understand the principle of how it works, where it just appeals to the straight line, which is the tangent, finds where it crosses the x-axis, use that as your new x value, that generates a new tangent, and you run down. When you understand the mechanics of it, the Newton-Raphson should make more sense. At least I'm guessing it'll make more sense for you guys. The second last section in this chapter has to do with just velocities and accelerations. Always start off with giving yourself an example in your mind of a speed of a car. Let's say 30 kilometers per hour. You'll say speed. You can forget this at the moment now, because you've just set up what you needed. So we're able to say speed, which you can call velocity. However, technically it's not velocity. And kilometers measures distance, and hours measures time. Now, if we were dealing with constant acceleration problems, then you will have a simple constant scenario. Most scenarios of cars, whether you're being driven to school or by, let's say, train or by bus, or whether you're cycling or whatever it isn't a constant velocity problem. You can state that at some times I have more velocity than another time. At some times I find that we're being accelerated, other times deaccelerated, and it's not even at a regular amount. It varies a lot. In the exact same way, when we were dealing with the start of differentiation, where it was seen that there isn't a constant slope for a curve, but we start off with the concept that you can pick 2 points and find the slope between them, we can state that this general style of looking at things can be employed. And what it's basically saying to us is that we'll call it velocity because the book does. Distance over time, we can say dx dt. We're now using the little d's again, which is the first letter for the del, so it clearly means we're dealing with differentiation. What this tells us is that at any instant in time, the velocity, which is a function of the time, can be found by differentiating the distance function. We also would know that acceleration is the rate of change of velocity. So over here on the right hand side we could have said and in calculus sense and we know that is the d dt, and we're going to bring this down here all straightforward stuff. And there are some very nice little problems in relation to this. Now clearly this is just talking in terms of cars and stuff like that and speed. We can apply this reasoning to volumes and loss of volumes in, let's say, cylindrical or conical containers. What we are basically putting across is the concept of instantaneous change. Here, velocity at any point in time is the instantaneous change of distance with time. Acceleration is the instantaneous change of velocity with time. An example. And the question is, find the 2 times the particle is at rest. This is a distance function for a particular particle. We know that velocity is dx dt, what you will notice is that it's only for a small little bit that you're actually doing calculus. It's the setting up of the problem, and after that then you're back down into good old-fashioned algebra, and you guys should be experts in algebra at this stage. In the chapters there are a lot of very interesting problems that you get, and the only real issue with them is to develop your equation. Now the second example from Rowntree's book is the one that should hopefully help you be able to do that. We'll draw it. Again, there's a particle and it's moving along a particular path. Applications 4. Y equal to x plus 4. So we know the slope is 1 and the intercept of the y-axis is 4. It then says when the particle is at point xy, which we can put up here, saying L is the distance to the origin. And they want you to show and if the second part is going to be very interesting because there's an important lesson for you to learn in this. Let's set up our equation. We know that L is going to be the square root of x squared plus y squared, which is the square root of Okay, that's the easy bit. You've set up what you wanted. That L is equal to this particular thing. We want to work out dl dt. Notice how we are in a situation where L is only known with respect to x. Now at this stage you can remember your chain rule. We could say dl dx. Well, it's equal to itself multiplied by 1, and 1 is any number divided by itself other than 0, so we can say it's dl dx by dt dt. And we can swap around these two just as you would in the chain rule. So you can say it's equal to dl dt by dt dx. Sorry, I skipped one line too far there. dx dt. We know dx dt. Okay, so that's our dl dt. When he wants to find it, for example, when x is 0, or even when x is 1, when x is equal to 1, that implies dl dt is going to be equal to no. Fundamentally, your job in constructing the equations is a job where a drawing is essential. In many cases you find that you're back to stuff that you've known for many years. Use Pythagoras, or what you can find is that you will need to appeal to, we'll say, the volume of a cone, or some function that you know and have known for many years. And your whole idea is, once you've come up with a volume in relation to a particular variable, you can always differentiate it. And we could have used this had we wanted to, but in this case they actually gave us dx dt. With this you can solve problems such as a conical tank with a hole at the bottom of it. It's filled to a certain height, and the rate at which the water exits the particular cone needs to be worked out. If you know the relationship between the height of the cone and the amount of water that can go out, you can actually work out the rate at which the surface falls inside and the rate of volume loss. Now, it's interesting stuff. It's just one example. There's a whole load of examples of things that you can do now. Even though there's only about 2 pages, 3 pages in any of the books on this part of calculus, what it should be doing for you is showing you that you've just arrived at the door of being able to solve a myriad of problems. Now, it's unfortunate that you'll have to wait till after the Leaving Cert, but it's nice to know that you have actually arrived at that, and that this stuff can really just light up and you can take off with it. Now, there's one last little thing, and it's the issue of the periodicity of a particular function. And for example, if we have something seriously complicated, when you're looking at a function, the easiest way to look at this is to say, right, that certainly looks like it's come back to itself, and it has. Does it repeat? And you find the answer is no. So it can't be this amount. You can go to the next big bit, which would be to say that amount going across to here. Will that repeat? And you find, oh, it's reflected, but that's no good to you. So you'd say it's not this amount. You need to go along until you find, for example, that distance. You know it's dropped, risen, dropped a lot, risen a little and down and back up. So what's it doing over the far side? Dropped, that's like that, gone back up, yes, gone down a lot, like that, gone up like this, back down, yes, and back up. So we would say that that's the period of it. Naturally, if this had actually occurred right on the y-axis, we could have said that even though we've sum of the function on the left of the axis, we will see we can get a period which would just start from here. but fundamentally that makes no difference. The whole issue is we're looking for one piece that we could cut out here, and that if we had put paint on it and made it into a stamp, you could stamp all of the rest of the function. It just repeats. You start with a smaller amount, where you do definitely see a pattern and see, is that the pattern that repeats? It doesn't take long to find out if it's true or not true. Then you just move up, and you just keep moving up until you find it. There's no real intellectual problem in relation to this. It's just that the equations that you may get in the exam could well have a periodicity to them, and you just need to be able to identify that. Now, you've arrived at the end of this chapter. There are a lot of, certainly in Rowntree's books, there are a lot of very interesting questions, especially related to the rate of change, which is just the last subtopic that we had there. It is worth your while to practice some of those, because you will not only be gaining practice, but they're actually interesting. We will be moving on to the further calculus and series in the next talk, and once we get, there'll probably be 2 of those talks, and once we get through that, we'll be on past questions. And when we get into past questions, you will find that we will get through quite a few of those rate of change kind of problems, and it should start to make more practical sense to you. But right now, you guys have very nearly reached the end of what we'll say the core of the course. There are a number of smaller sections which I haven't covered yet, but this particular core, which is algebra into geometry, complex numbers, trigonometry, an understanding of vectors, and leading us across into differentiation, integration, and special question. It's like a core. It's a big core. Oh, sorry, I forgot series and sequences are in there. They are so useful one to the other, and particularly when you get to the special question, you will find that it should become easy to you now. You have covered almost every single thing you need to cover for it. Okay, we'll leave it at that, and I'll see you the next day.